Propositions symbolized in our logical system are truth functional. What that means, of course, is that their truth value, whether they are true or false, is determined completely by the truth value that one assigns to the atomic components that make up the sentence, and also is a function of the order or position or arrangement of those atomic sentences, as well as the arrangement of the connectives that bring those together to make the complex sentence. Now, this fact allows us to determine a certain number of properties about both propositions and arguments. In regard to propositions, we can determine whether they are tautologous, whether they are self-contradictory, or whether they are contingent propositions. And we can compare two propositions to determine whether they are equivalent or whether they are contradictory. And perhaps most importantly, with an argument, we have the power here to determine whether or not it's valid. We can do this by relying upon the characteristic truth tables of the different connectives and by arraying or displaying the entire set of possibilities of truth value for each of the atomic components of a given sentence. That way, what we have done through what's called the method of truth table is to, in effect, give you all of the possibilities for the truth values of the components of a sentence. And with that in front of us, we can then compare sentences to find out, for example, if they contradict each other. And we can also determine whether the premises will lead to the conclusion, whether the conclusion follows validly from the premises, by pointing out that there is no possible arrangement of truth values which will make the premises true but the conclusion false. If you recall the definition of validity, you'll know that that fact will ensure that an argument is valid. So it's the method of truth tables that we're going to be looking at here in Unit 9, and we're going to be applying that method in its various forms to these different questions about some of the properties of individual propositions, some of the comparisons between propositions, and then the question whether an argument is valid or not. So we can begin now, and I'll show you how to assemble truth tables. Use truth tables to determine, in these cases, whether the following statements are tautologous, self-contradictory, or contingent. And our first example is A or B hooks A and not A. Now, the first thing that we need to do is to fill out the truth table, and we begin doing that by assigning all the possible truth values to the different atomic sentences. You have to do this in a certain order in order that the entire table work out properly. So let's look at how we've begun here. We've already got the beginnings of the table here on the page. Notice that the atomic proposition A can be either true or false, correct? So can the atomic proposition B. But since now we are trying to bring together these two atomic propositions, there are four possible combinations of truth value. A can be true and B can be true. A can be true, B false. A false, B true. Or both of them can be false. A nice way, or a little trick of making sure that you arrange these the same way every time is this. Start by generating a column under the first atomic letter, in this case A, and think about dividing the column in half, assigning true to the top half and false to the bottom. Then when you move on to the second atomic sentence, think about dividing those halves in half. That is, assign true and then false to the top half, true and then false again to the bottom half. And we'll see how we can elaborate this when we go on to even more complex examples. Now notice when you have recurrences of the same atomic sentence within a larger complex sentence, as we do here, notice we have A here and also here, you have to assign the same truth value on each of the lines. So you will see that this column here simply repeats the column under A. Now we can move ahead and fill out the rest of the table. Well, we know that if A has these truth values, then not A, its negation has to have the opposite truth values. And so under not A, we simply put false, the opposite of true, false, true, true. Okay, now we can start doing the columns that were required underneath the connectives that bring together these atomic sentences. And here again we have to use the idea of the main connective. Remember now, this conditional, this hook here, is the main connective. It's bringing together this unit, A or B, with this conjunction, A and not A. So we have to work from inside out, which means that the first columns that need to be developed are the ones that bring the units inside the parentheses together. So let's start over here. We have to generate a column under the OR sign, which in effect gives us the result of disjoining the two truth values that we see on each of these rows. So think of the characteristic truth value for the disjunction. If you bring together a true and a true, true or true has the resultant truth value true. True or false, true. False or true, true. And the only condition under which a disjunction is false, the double falsehood of the elements, gives us false there. With conjunction, remember, one false is sufficient to generate a false conjunction. So this line would be false, 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 false. Now we need to generate the last column. This is the column under the main connective, and it in effect brings together the column that's under the disjunction and under the conjunction, because these are, as it were, the next level of connectives to generate the sentence. So we need to ask what a true antecedent and a false consequent in a conditional generates. That, you'll remember, generates a false conditional. And so once again we've got true, false here, so the answer is false. True, false there, and false, false here. So the answer on that last case is true. Now we need, with the whole table in front of us, to determine if this sentence is tautologous, self-contradictory, or contingent. You should recall now that a sentence is tautologous just in case it is true under every different assignment of truth value to its atomic components. That is, every row here has to have a true. We'd have to have true, 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 true for a sentence to be tautologous. Well, clearly we don't have that. Is the sentence self-contradictory? No, because to be self-contradictory, every column has to be false. And here we have this last true. A sentence is contingent just in case it has some true values and some false values under the main connective. That's our situation here, and so this sentence number 1 is contingent. Now you may notice here by doing this that this is a very rote, or what mathematicians call algorithmic system. It's quite mechanical. There's not a whole lot of high-order mental thought going on here. But this is actually one of the advantages of this method. You've got something which is so mechanized that it's very simple to ensure that you haven't made a mistake. And now we're going to take these same procedures and work through a couple of more examples that are quite similar. You'll see we're just repeating the same kind of methods, but we're applying them to slightly different questions. So here's number 2. We have a complex conditional statement with a conjunction as its antecedent and another complex conditional as its consequent. And we need to determine if this is self-contradictory, tautologous, or contingent. Once again, recall, we begin by arranging the columns under the different atomic elements that are involved by, in effect, breaking those columns in half, assigning true to the top half under A, false to the bottom half, then breaking those halves into, you get 2 trues under B, followed by 2 falses, 2 trues, 2 falses. Then we take those halves and have them once more, and under C then we get the repetition true, false, true, false, true, false, true, false. You'll notice that this then presents us with all the 8 possible orderings of truth value for the combination A, B, and C. And recall, as I said before, you have to repeat the same truth values where you have repetitions of the same atomic sentence. So each of these will have the same truth value as occurs under the first C. So these are easy columns to do. And now we work from inside out, having identified this conditional as the main connective. So that will be the last column that we fill in. Well, what's next? Either we can do this conjunction, or we could do this conditional here. Let's do this conditional since we're in a sense working, this is the deepest part of the sentence, we'll work our way out of the brackets. So we have a true hooking a false, or that is a true antecedent and a true consequent to the conditional under this assignment. That, of course, gives us true. This gives us true because of the false antecedent. This is true. 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 And this is true. Notice, remember, we'd have to have true, false in order to generate a false in this column. Okay, now we need to take the values under this C and hook them, as it were, to the values under this conditional. So true hooks a true is true. False hooks anything is true. True hooks true, true. False hooks true, true. True hooks true, true. False hooks true, true. True hooks true, true. And false hooks true, true. Notice we could have predicted that because under this, the consequent, we had nothing but trues, therefore eliminating the possibility of a true-false antecedent-conditional, antecedent-consequent arrangement, which was the only one that would give us a false. So we have that done now. We can do the conjunction. Remember the characteristic truth table. The conjunction will give us true, true, false, false, and all the rest are false. And now we're almost done. We simply need to bring together, under a conditional, this column with this column. So we have true hooking a true, which is true. True hooking a true, true. False 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 hooking a true. This gets a little repetitious. And false hooking a true. Now notice the interesting feature of this column. It's a column of trues. That's the situation under which we have a tautologous sentence. It's a sentence that is true under any interpretation or any assignment of truths or falsehoods to all of the components of the sentence. Okay, now we're going to move on and do something slightly different. We're going to apply this principle or this method to the question whether a pair of sentences is either logically equivalent, contradictory, or whether they're neither of those. And here's our first. We've got, as you see here, two sentences, D and F or G, and then I'll just put a little break sign here. And the other sentence is D and F or D and G. First, we have to fill out the truth table before we worry about deciding if it's equivalent or contradictory or neither. And again, it's the same principle as we have been using. So, in fact, instead of filling out all of the columns under the repeated D's, F's, and G's here, I think I'll just leave them and we'll see whether we can shorten this down a bit. So let's start over here. We need to bring the F and the G together with a disjunction. That will give us true, 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 false. Remember, two falsehoods there. True, 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 false. Now, the D must be conjoined with this column, the column that we just worked out. So we have true and true, which is a true, true and true, true and true, true and false, false and true, all the way down here, and false gives us false. All right, so we have one sentence finished. This, remember, is the main connective, so this is the column that will be of interest to us. Now we need to do the same thing over here, bringing together the truth values for D, conjoining them to the truth values for F. Now, as I said, we don't need to write these down here again. If you wish, it would be perfectly fine to do that, but we'll just speed things up by referring here to these columns because they're going to be identical to the ones that would occur here. So, T and T is true, T and T is true, T and false is false. Okay, see, I followed this column and conjoined them together as is indicated by this part of the sentence. Now I need to conjoin D and G, so in effect need to bring this column into conjunction with this column. So that gives us true, false, true, false, 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 false. Now the main connective of the right-hand sentence is the wedge, and we will then need to bring together, under the disjunction notion, these two columns. So true or true is true, true or false is true, false or true is true, but this is false, this is false, this is false, this is false, and that is false. All right, so we have, in effect, done. We've abbreviated a bit, but we're, in effect, finished with the table, and now what we need to do is ask, are these sentences equivalent, are they contradictory, or are they neither? Well, two sentences are equivalent if they have exactly the same truth value, no matter what arrangement or assignment of truth values is given to their atomic components. That would then mean that for each of the rows, we would have to have the same truth value. So if we have true here, we must have true here. If we have false here, we must have false here. So let's go down and have a look. True, true, that's okay. True, 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 true. False, false, notice the same, that's good. False, 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 false. So that's just the situation in which the sentences are equivalent. For whatever is on this column must be repeated under the main connective of the other sentence. Notice if it were contradictory, then what we would need is two columns, this one and that one, being the obverse of each other. That is true, false, true, false, true, false, false, true, false, true, and so forth. And if you have a mixture, that is sometimes the columns show the same truth value, but other times different truth values, then the correct answer is neither. Okay. Now on to something even more interesting. This has to do with determining the validity of the argument. This really, I think, is the power of the truth table method. We have been working out ways of stating and symbolizing arguments. We've already introduced and worked a lot with the concept of validity, and now we're bringing together this idea with the truth table method and actually coming to see what some of the benefit of the system is. The benefit, of course, is that you could now symbolize an argument that was given to you, and then you could form a truth table on that argument, on its premises and conclusion, and see whether the argument was in fact valid or not. Well, we'll see how we do this now. Here's an argument with two premises, and this conditional as a conclusion. Now, how do we construct the truth table to show that on the assumption that these are true, the conclusion follows? Well, we first need to lay out the two premises and also the conclusion, and in effect count the number of atomic variables that are involved here. Notice here we have three, don't we? E, F, and G simply repeat through the premises and conclusion. That tells us that our truth table will be 2 to the third lines long, or 8 lines long. In other words, there are 8 possible alternative arrangements of truth value. And that's what we have shown you already how to do. You take the 8, you make a box of 8 in depth, and you break it in half, giving the first 4 the truth value of true, the last 4 false. Then you take those halves and vary them, so we get true, true, false, false, true, true, false, false. And then under the third, you vary from true to false with each case. True, false, true, false, true, false, and so forth. Okay, and remember now, then under these, you will simply have repetitions of the values as they've occurred over here. I could fill them in, but we'll save again a bit of time and not do that. Now we need then to figure out the columns under the connectives. So let's begin with the first premise here. We notice that the conditional is the main connective, which means that we'll need to work out the disjunction column first. And we'll remember now that that's true under every condition except where both of the disjuncts are false, like here and here. Now we are, in effect, hooking this column to this column, the G. All right, so we have T hooks T, which is true. True hooks a false, which is false. And this is true. This is false. This is true. False. True. True. All right, so we're done with the first premise. Now we need to generate the boxes for the second premise. We need to conjoin E and F. So we need to bring together the first and the third columns under the sign of conjunction. So that's going to give us a true, a false, a false, 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 and false. Now we need to look at the column under G, which of course will be the same as this column, and we need to hook that to the column we just worked. So we're bringing this column and this column together under the conditional sign. So true hooks a true, false hooks a true is true, true hooks a false is false, false hooks anything is true, true hooks false is false, true, false, true. Okay, so we have the two premises done. Now we need to work out the conclusion. Same thing, start from inside and work your way out. So let's do this disjunction first. That, of course, will be the same as the result we got in the second column, since that was E or F. So we can simply copy over this column, true, 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 false, and false. Now we need E and F, and of course that's identical to this column. So let's just write it down here. True, true, false, all the way down. Okay, now this is the main connective, the conditional, and so we need to hook these values to these values. And the result then would be true, true, false, false, and the last two are true. There we are. Now that is the table. How do you determine whether this argument is valid or not? Well, remember the definition of validity. If you assume the premises to be true in a valid argument, then the conclusion's truth follows with necessity. That means it's impossible that there can't be any assignments of truth values which make the premises of the argument true, but make the conclusion false. So what we need to do is to simply examine the table and find out whether there is any row that makes all of the premises have a truth value of true, but gives the truth value false to the conclusion. So if we return to our graph, we need to compare then the columns under the main connectives, that is this column here and this column here. Right, those will indicate the premises' actual truth. And we need to compare them now to the value that's given on the same row under the main connective of the conclusion. And we have to watch that we don't have a row that goes true, true, false. That would show that we have invalidity. So the first column is fine. The second column is fine because this falsehood here keeps this column from showing that the argument is invalid. Remember, to show that it's invalid, you have to have all of the premises true, but the conclusion false. So this one, again, is no good because of this premise. Again, no good. No good there. No good there. No good there. And no good here. Notice here we've got both premises true, but when they are true, we find the conclusion also is true. So, failing to find a row that says true, true, false, where the premises are true but the conclusion false, shows us that it is impossible to assign truth to the premises but falsehood to the conclusion. Since that's impossible, the argument must be valid. One additional method is going to be covered in Unit 9, and that's the method of indirect truth table. We've already noticed that it's rather laborious to fill out every cell in those large matrices. And in fact, if you consider other kinds of arguments that would involve more atomic variables, for example, 6 or 7 instead of 3, increasing the size of the matrix geometrically, then you would realize that this sort of method is less efficient and certainly considerably more boring than we're going to see the method of indirect truth table is. This is an idea of abbreviating the whole table, but getting the same result. In other words, still being able to decide whether or not an argument is valid or invalid. So let's get a problem up here and see how this method works. All right, here's our problem. Notice we've just simply stated the 4 premises here next to each other, separated them with a single slash, and the conclusion of the argument is separated from them with a double slash, so the conclusion is not M. Now reflect upon the concept of validity again for a moment. If an argument is valid, it's not possible to have an assignment to the premises that makes them all true, but an assignment of false to the conclusion. If you could do that, then the argument would surely be invalid. Now, the method of indirect truth table starts as an attempt to assign just that assignment, that invalid assignment, to all the premises in conclusion. So what we need to do is begin with the assumption that the conclusion of the argument, not M, will be false, and all of the premises will have the truth value true. So we need a true under the main connective of each of those. So we'll need a true under the tilde. We will need it under this conditional, and under this conditional, and under the last conditional. So here's what we're trying to do. We're trying to fill the row out so that the premises are true but the conclusion false. The question is, can we do this? If we can do this, then we have an invalid argument. If we get stuck, if we can't consistently fill this row out, that will show that the argument is in fact valid. Now, let's return here and see what we already know about this row. Notice that if the conclusion must be false, then the M must be true. That will tell us that the occurrence of M over here also must be true. Now, look at the first premise here. If it has to be true, since it's the negation of a disjunction, the only way that would be possible is if the disjunction itself were false, and remember that requires that both the R and the P are false. That tells us that this P here is false, and this R here is false. Now let's see what else we can learn just from the values that we already have down. Notice this conditional here. This has to be true, but it has a false consequent. Therefore, we know that Q can't be true. If it were, this whole thing would be false. So Q must be false. Notice that tells us something more about premise 2. Now the question is, can I generate a line on which P and Q are false, but this whole premise is true? If these are false, the disjunction is false. If this entire conditional is true, then the N must be false in order to make that conditional true. That means then the N over here must be false. And now we have to ask whether we can fill out this remaining premise in order to make it true. Well, we have a true antecedent, and we have one false disjunct of a disjunction. Is there a way of making this disjunction true so that the entire conditional here will come out true? And of course the answer is yes. If O were true, then N or O would also be true, and then we'd have M hooks this disjunction, true hooks true, and that would be true. So notice what we have now accomplished. We have generated a row. Every atomic sentence here has gotten consistent truth assignments, such that each of the premises have turned out true, but the conclusion has turned out false. Therefore, it is possible to assign truth values to all of the atomic components of the premises in conclusion in a way that indicates the argument is invalid. If the argument were valid, we would get to a point at one of the premises or another, someplace on that row at least, where we would need to have the one truth value, but would be forced by what we already know to place the other truth value. In other words, for example, this would say have to have been false, let's say. Or a better case, take this M. This M would have to be false. If it needed to be true in order to make the entire premise true, then we couldn't assign it false, and therefore we would be stuck, as it were. When you're stuck, when you can't assign it, you place a slash through the truth value that is impossible, and you then know that the argument is valid. Now, one final trick here. Some of these indirect truth table problems require that you generate more than one row, because it's not always the case that you get enough information from the single row, as we just worked out, to indicate that the argument is in fact invalid. This situation happens, for example, when you have a lot of disjunctions occurring in the premises. You need to read about this complication in the book, but you generally don't need to go over 2 or 3 rows in order to ultimately determine whether in fact the argument is valid or invalid. So have a look at that stuff, and good luck on Unit 9.